Welcome back, Tink fans, and in this video we're going to continue our series making some custom new LCD gauges for my Nissan 350Z. In the previous part we dove into Figma and designed these three gauges. They're kind of in the ballpark of what we're going to do, and in this part we're going to take on probably the most interesting of the three, the Speedo RPM gauge, and code it using LVGL for a 2.1 inch screen. At the end of this, the result will look like this, and we'll have the ability to accept the incoming data for the RPM, the speed, and the gear, and change the visual accordingly. We are going to be testing a new format of doing this video, so if you like it, please let me know in the comments, because I'm trying to refine how we make these videos going forward so they're more useful for you who wants to learn how to do this really cool technology-based stuff. A note before we dive into this is that in order to use these WaveShare 2.1 inch touchscreens, we need to use either Arduino IDE, which I don't really use anymore, or ESP-IDF setup, which is what we've got going on here. I'm not going to delve into the entire setup because it's not important at the moment, but all we need to know is that ESP-IDF provides us with a bunch of functionality like you might get in Platformio. So if you look at the bottom of the screen, we've got things like do our build, which compiles all our project, Flash, which uploads everything to the board, and then monitor, which obviously we can use for serial monitoring. Then this one, build, flash, and monitor, which we use a lot during this process. So compile the code, send it all to the board, and then monitor it. So that's one we use a lot. But what I'm going to do in this new format is, instead of like going through and coding it a line at a time and showing you how I do it, is we'll break it down a section at a time, and I'll run through the code that creates that section. Reason is, yesterday I recorded this entire video, breaking it down by typing it one line at a time, and it took me 5 hours to film, and I've edited half of it, and it's currently 90 minutes long. It's too long. It takes too long. So I think this new way will work. The big thing that you need to know about this setup is that two things have really happened. The main C file here, I've added a build UI, and I've included it with this Speedo demo. Then the Speedo demo files are here, so the H file has just got the included build UI function, and this C file is where we're going to be including everything. There are a few clever things that I want to do for the development of this board. I want everything to be relative to the size of the screen that it's on. So if we wanted to use a smaller screen and use this gauge on a smaller screen for something else like boost pressure, we could do that just by changing a few global values. So everything's got to have relative sizing. We want to think a little bit about reusability, so things like styles that get repeated, making sure that we don't need to rewrite those bits of code multiple times, and just generally future-proofing the project so that we can expand on it or reuse elements of it in the other gauges and save our time in the future. To begin with, we're just going to flash the device and get rid of everything that's currently on there. A nice blank screen from which to start all this development. And at the bottom left of the screen, you'll be able to see what we're currently working on, what stage of the design process we're on, so you can see how I would design this in an iterative way. So there we are, blank white screen. That's where we start from. For part one, we've just added a black screen background. This is just covering the entire screen and is going to be the element in which all of our LVG elements sit inside. We've created a global component as screen, which is just an LV object type. We've created a global color. So first of our color palette, which is palette black. We've created a global dimension 480 because this screen is 480 by 480. We haven't actually used it at this point, but we're going to a lot. And then at the start of our build UI, we've said that screen, this global variable, is a LVGL screen active. So it's a new screen and it's active and it's on the page. And then we set its style background color of screen to palette black, and 0 is just setting it to the main. So each LVGL object has multiple parts. 0 is like the main, it's the all-encompassing, so it's just set it to black. So it's a black background, and that is set on the page. For step 2, we've added the arc, because the arc is the thing for which all the sizes of everything else will flow. If it's too big, too small, all the other elements have to be sized due to it. So at the top, we made the arc, the moving arc, another global component, because it needs to be able to be set by things outside from itself, because there's something that's going to be pinging data to it to say, set the value to this. If it's self-contained, it doesn't need to be global, but this isn't self-contained. It needs to be a global value. So we've got this global RPM arc. I've expanded out the color palette to use all the colors that I'm going to use for this entire project. So amber, black, red, and white. So they're just defined here using the LV color make function that is provided as part of LVGL. And I've introduced a bunch of different variables that we can use. If you're going to use this, you can play with these numbers and it'll adjust the way that the gauge looks. So if you want to use it on different size screens or change the thicknesses of everything, it's all done here and everything's going to be done relative to these numbers. So dimension is the exterior, the outskirts of the screen. That's how big the screen is. My RPM max is the RPM max that my gauge goes to in the drivers cluster, so 8,000. The arc width is how fat the arc is. I've gone for 24 pixels. The arc size is dimension minus 50. This will change, but at the moment, what I've done is made it so that it is 50 pixels smaller than the screen. So it doesn't go all the way to the outside edge. It's just inset a little bit. An arc start and arc end are used for the position of the arc. So when looking at the placement of an arc using LVGL, 0 degrees is 3 o'clock. So over to the right. Then it goes clockwise. So the very bottom of the screen here is 90 degrees. There's 180. There's 270. So I wanted it to be a bit after 90 and go all the way around and be a bit before 260. So what we've actually ended up using is, as you can see on these numbers, 120 and 344. 344 was done quite specifically because that means this entire thing, so 344 minus 120, the sweep is 224 degrees, which happens to be a number divisible by 8. And I want to divide this into 8 sections with like little markers. So it made sense to do a whole number. It doesn't need to be a whole number, but just for like sake of simple mathematics when it comes to dividing. But we'll see about that in a minute. In the build UI function, we've done this, make the arc, and this is the code that creates that arc. We define it as an arc using LVGL and we attach it to the screen. We set the size of it. So every time we use one of these LVGL functions, doesn't matter which one it is, we always have to name the component that we're using it on first, and then the attributes that that function takes. So set size of the arc to size by size, which is our arc size here, dimension minus 50. So the size is how big it is on its outside edge. So this is actually 430, there we go, 430 by 430 pixels. The alignment is the LV align center with an offset of 0, 0. So bang center in the middle of the screen means it's even around the edge. The angles, like I said, we start at 120, so just to the left of bottom, and we end at 344, so just north of like east. Then an arc is made up of 3 parts. Main, which is the background behind the arc, the moving arc part. Indicator, which is the bit that you see, the moving part on top. And knob, which is the round button thing that would usually have your finger on that indicates where you're going. What we've done is styled the background one as black, so you'll never see it, but it is there because it's the same color as the background in my page. The foreground one, the indicator that we can see, is amber. We've added a false flag to rounded, which gets rid of the round edges on the end of the arc and makes them flat. And we've set its width to be whatever I want the arc width to be. So up here it's 24. If you wanted it to be fatter or thinner, you would just change that 24 to a smaller or a large number. Then I've removed the style of the knob, which has completely got rid of that. And then we set the arc range. So outside of the angles that it goes to, you need to set what the min and max values are. And that's what this is doing really. So our min and max values for this arc are 0 through to whatever the RPM max is, 8,000. And then I'd finally use the set value function to set it to 8,000. It's obviously not generally going to be at 8,000, but it makes sense because then we can see where it's gone up to. And that's how we build the arc. Part 3, adding the little white border on the inside. To do this, we add a new global variable, one of our attributes, with the RPM line width is what I've called it. So how fat the line is. For this, we've gone for 4 pixels. Everything else up here has stayed the same. The arc is unchanged. We've created, again, another function as part of our build UI to make the RPM border. And in this, we've got a bunch of code that is very similar to what we've just written. We've got the creation of the arc here. It's, like I said before, doesn't need to be global because nothing is going to affect this in runtime. It just gets built onto the page once as the page starts up, and then it doesn't get affected again. So we can just build it as part of this component. Then we set the size. This is the only one that looks a little bit complicated, but it isn't. So we just needed to mathematically figure out where the outside edge of this white circle goes. And it's basically the outside edge of this circle minus twice the width of this arc minus twice the width of the line, because I'm making sure this gap is equal to the size of the line, of the width of the line. So they all like flow nicely and have good rhythm. So what that means is the size is the arc size minus twice the arc width minus twice the line width. And we've got that both for the horizontal and the vertical height. Then we again line it to center just like we did before. We start the arc at the start and end positions, exactly the same again as before. The difference we have this time is we've hidden both the knob and the indicator because we don't need to show the indicator for this one. We've just done all the styling with the main, which is the background. So we've made it have our line width for its width. Again, we've put a false flag for the rounded and set its color to the palette white. And that gives us this layout that you can see now. Part 4 is perhaps the most interesting part of this makeup, and it's the RPM markers that show every 1000 RPM on the gauge. We've added a new attribute at the top of the page, which is this constant float. It has to be a float, not an integer, because otherwise if it's like 25.5 degrees, it's not going to work. Nothing's going to line up properly. But we do our arc end minus our arc start, which gets the number of degrees of the angle that the arc is, and we divide that by our RPM max divided by 1,000. So in my case, it's 8,000 divided by 1,000, so it's 8. So it's the angle divided by 8, which gives us a final value of 28. I don't think it's going to show this here, but oh, there it is, 28. And it has to be a float, like I said, because it might not be a perfectly round number. If this was 340, that would be 27.5, not 28. So a float number, and we have to cast one of these to a float because these are all integers. And if we don't cast to a float, it's going to process them as integers, even though we've told it it's a float. Thank you, C++. Then at the bottom of our border function that we've just created, I've created this little extra section. So we say, how many markers are we going to need around this gauge? And we're going to need the number based on the RPM. So in this case, 8,000. So that's 8 markers plus 1. And it's the old posts versus fences conundrum. You need one more set of posts than you need of fences, because we have 1 marker at the end of every of the 8 1,000 markers plus the one at 0. So we need 9 as a total. So we can just do that with a quick calculation. So the RPM max divided by 1,000, add 1. Easy. Then we create an array of objects, which is called RPM markers, and it's got that count. So we've got 9 objects in this array. And we do a quick loop through that array count. And for each one of those objects in the array, we just create it as a new arc. So these, even though they are little lines, they're actually just tiny little arcs. And then we pass them all one at a time into this new position markers. function, which is just above here. So it takes in the marker and the position. So like you saw here, you pass it in the marker from the array plus its position, which is I. We set the size. So the size is, again, how big it is. And this one needs to be the arc size add a little bit because we're making it a bit bigger. Now, this was just a draft image. I decided I wanted it to be 2 line widths wider than the outside of this gauge, as you can see. So it's the arc size plus the line width times 4, and it's got that in both directions again. And it's always double the number because you have to consider it's got to add it on both sides. Yeah. We align it in the center, just as we've done with the rest of them. And then the width, which how thick it is the arc width, so the big orange width, plus the line width times 4. Which means it's big enough to cover the orange arc, plus have 2 line widths above the arc and 2 below. So one that covers the gap and then one that goes actually onto the inner white edge. Again, we remove the rounded from it. Again, we set the color to white, nice and simple. I'll come back to the angles in a second. And then we're going to remove the knob and remove the indicator. The final thing is each one of these has to be dynamically positioned based on how far it is away from the start. So our arc start is currently at 120 degrees, and the very first marker will be bang on 120 degrees. So that thing we had figured out at the top, the marker gap, is how many degrees on each marker goes, and this one happens to be 28. But the first one needs to be bang on that 120. Whereas the second one is 120 plus 28. So that one will be at 148 degrees. So all we're doing is calculating its position. So position 0, position 1, position 2, times by the gap. So times by 28, which means our first one is arc start 120 plus 0 times 28. Whereas the second one that comes through will be position 1. So it'll be 1 times 28. So that will just find the start position of the arc. And then because we only want it to be a tiny little line, our end position is the same plus 1. So each one of those markers is actually a 1 degree wide arc. Just means everything easily focuses into the center point and all the angles of the line is right. It's a dead easy way of doing it. That's probably my favorite part of this. And so if you were to change around your values up here, it would automatically figure out, all of the dimensions. And so you could put this in a 10,000 RPM car just by changing this to 10,000 really easily. Part 5, our little red line marker at the end of the gauge. We've made a new function, make RPM redline. At the start, we've got a new constant, RPM redline, again, where we just set what value that is. It's 6600 as default in the 350Z. When I get it tuned, that'll go up to 7000. I could make it so that I can adjust that on the display. We're not going to do it today, but it's easy enough to change if you want to change that redline value. And then here's the code to actually make that redline. Much like before, you're going to be used to this by now. We've created an arc. We set the size to just be dimension by dimension, which means its outside edges right on the outside edge of the screen. The alignment is the center. The angles we'll come back to in a moment. Its width at the bottom is the line width times 2. By doing it as a multiple of the line width, it keeps nice rhythm of the sizes of things. I've actually done everything in iterations of 4 pixels, so that will have a nice flow. Again, we've removed the rounded edges by adding the false flag. We've made the color, the palette red, and we've removed both the indicator and the knob. Lots of things you've seen before, but the angles, obviously the very end point is easy. It ends at our end. But in order to find the start point, we need to do this little bit of mathematics right here. So what we're doing is starting at the start, and then we need to find out what angle 6600 is as a relationship to 8000. So if you use arc start minus arc end, that will give me the entire set of degrees. And then if we cast our red line to a float and divide it by max. So Redline divided by max gives me a number is like 0. This is actually 0.825. So it's 0.825 out of 1 of that angle. So it's 82.5% of that angle. So if we just take the total angle and times it by 0.825 and then add that to the start, that'll give us how many degrees on we are. Seems complicated. It probably isn't really when you take the time to just sit and break it down, but that's how we get our start point. And yeah, again, so if you change that 6600 to a bigger or a smaller number, then it will change how far around that red line is. Everything else from here on out will be much easier because it's just really labels and text that's moved around the screen, except for one interesting thing towards the end using custom canvases. Part 6, super simple one, just adding the RPM digital label over to the side of the screen. Just a couple of little quirks that we need to consider. First one being that because much like the arc that moves, something external is going to be changing its value. We're going to need to be able to access it in other subcomponents in the future when we get to that point. So we've made the digital RPM a global object, much like we did, like I say, with the arc. Then we've got a new function at the bottom. So we've created make the RPM digital. Here we've started by creating its style. So this style is basically just a regular normal weight font. And the one that comes with LVGL is called Montserrat. It's, I think, quite a nice font. And it's one I've actually decided just to keep using for this display. So we create a style. So this is the RPM style and initialize it. This is the code you need to use to initialize a style in LVGL. Then we apply the things that that style actually has. So it's almost like creating a style sheet. So this one, the RPM style, has a text font of LV Montserrat 40. Now that is included with LVGL and there are a bunch of different options. So if I was to change this, there are a bunch of different sizes. You actually do need to go into the LVGL settings and initialize the sizes that you want to use. Little preview of some stuff that I'm going to be doing here, but 40 is the one I've gone for this. And the color of that style is just my palette white. Then I've created that label, and like I say, because it is a global label, we're just initializing it here. Then we set the label of what the text wants to be. One quirk here, not quirk, but one thing to bear in mind is that it'll only accept char values. So it has to be a quoted string of text. You can't just pass it to the integer. That will be something we have to consider when we're setting this, because we are going to be receiving integer values that we're going to have to convert to a char on the fly. But that's simple. We'll get to that in a bit. And we add that style that we've created to the label by, again, doing it to 0, just applies it across the board. And then we align it. And you might think, oh, just align it in the center and then drop it off to the right. But if you use the center alignment here, so LV align center, we can do that, but it will mean the text is also center aligned. So as the numbers get bigger and smaller, it'll grow out evenly on both sides. Because I've got this, actually, the way I've got it aligned, I want the text to just flow. Left-hand side stays where it is, and the rest of it moves. So we stick with this left mid, which puts it in the middle of the screen on the left. Then we use 360, which pulls it all the way over to the right, and -10, which moves it up a little bit, because there is going to be a label below it. And if we just keep it bang in the middle with the label below it, the vertical rhythm seems a little bit off. So we just move it up a shade. That's our RPM counter. Step 7, a nice, big, bold speed taking up the middle of the screen, so there's no way you can miss it. There are a couple of interesting things here, mainly in the fact that the font that I've used, the bold Montserrat font, doesn't exist in LVGL, so we have to create it custom and import it into the build. Fortunately, there are a couple of tools that make it really easy. LVGL actually has access to this tool. I'll stick a link to it in the description, where you can come and create your own font. So you name it whatever you want. You tell it what height it's going to be. and then you upload the TTF file. If you want to use Montserrat, the default one, you can actually go into Google Fonts and download it. And from here, you can get it in its variety of different weights. I went and I created a few different fonts that I want to use both for this bit and for like the little labels. And in this fonts here, we have the C files that you download from that font pages. So it'll give you them as a C file, but you actually need to produce them in here as a H file. So this is the code that it produces for you. So you can just drop these in here and then include them in the top of your C files here and include that font, and then it's just ready to use. It's pretty simple. Again, this is going to be a component that needs to be updated from an external source, whether it's a GPS monitor or the ECU that's providing the speed information. So we make it globally available. And we've got this new get speed digital function. It's almost identical to the RPM one. We create a style for this speed text, which is this bold font that I've just created, Montserrat Bold 120, and the color is white. We create the label. We set the text again as a string or a char to 85. We apply the style to the label and then we align it bang in the middle. So this one is dead in the center, 0, 0. So this one will expand out like that, but probably the majority of the time it's only going to be in the 2-digit format. So it's not a problem unless I'm track daying or on the Autobahn. Fun. Step 8, the miles per hour and the RPM labels underneath their respective parts of the display. One thing that we had to do here that was different to what we've done before is there's no point creating the style twice because we want the style to be consistent across the two. So at the top of the page, we've included the 28-point font that I've used for this. Like I said, I've been doing things in multiples of 4. So the big bold font in the middle of the screen was 120. These ones are 28, so they're smaller. And then we've created a global style of the unit text. So it's something that I'm going to reuse across a bunch of these different screens, and it means a lot of this component page we can use for the next gauges when we come to create them. Then we've started at the top of the build UI. We've got this make styles function, which is at the top of the page here, and it just initializes that global style and sets it to what we want it to look like. So it's going to use that bold 28-point font, and it's going to have the amber color. So that's really simple, but it then means style unit text is available for any of the labels that I want to use. So when we come to our RPM digital, we literally just create a new label, which is, just a label type. We set the text to RPM. We add that global style to it. So then it's got the orange and it's got the bold 28-point font. We apply it to everything and then we align it in the correct position. So again, it's from the left-hand side, it comes in the same amount, but then it goes down 20. So the left side of the RPM value and the RPM label are always going to be aligned. It'll keep things looking really nice and neat. And then with the speedo bit, we do almost identical code, except it uses miles per hour and the position is relative to the center as opposed to relative to the left-hand side. You could do either, but it was easier in this instance to do it from there. And it's 40 pixels across and then 60 pixels down to get it where it is now. Sometimes when you're doing this stuff, you have to just guess and get it in the right ballpark. So start at the center and then add like 30 and 30 and get it like down there a little bit, and then just tweak those values until it's in what feels like the right spot. That's exactly what I had to do here. There's no way you're going to get it exactly right the first time. And for this last-ish point, the gear notification at the bottom of the gauge. By now, you see me create enough of these elements that you should realize pretty much the process we need to do, but there's one thing that's a bit of a quirk of the development of this. We've obviously got a new font in there, so it's a bold 80 pixels. Like I say, iterations of 4. We've got the gear label as a global thing because it is going to have to be affected by an outside source. It's going to be my hall sensors that tell me what gear I'm in, even though I'm in a manual car. And then at the very bottom, we've initialized, as part of our Fastboy stuff, the speed, and we've got the gear here. And there's one thing that's a little bit interesting, and it's when we created this design, I had the tops of this like square behind the background of the gear like come in slightly. It's a slight trapezoid. In order to do that, we need to use a canvas element and then draw the corners of the thing inside that canvas. Fortunately, it's not that difficult to do. So we start by defining the space in memory. So this basically is setting a 120 by 120 pixel space in memory in order to create that canvas. Then we create a canvas, so a canvas creation on the screen, and we set that into memory. This is just basically the silly process you have to go through for creating canvases with custom stuff inside them. Then we align that canvas relative to the center, straight down. So 195 pixels like drops it right down to the middle. Then we're going to create points, and the points are relative to the canvas, which is why we need to do the whole memory thing. So the top left point is 15.0, which means it comes in 15 pixels from the top left, but doesn't come down at all. Then the top right point is 105.0. So because it's 120 pixels wide, 105 is 15 in from the top right. So we've got 15 in from the top left and 15 in from the top right. And then two bottom ones, 120, 120 is the bottom right. So that's bang in the bottom corner. And 0, 120 is the bottom left. So they're bang in the left corner. So it goes around from top left, right, bottom left. Then we're going to create a draw type. Unfortunately, you can't just use the style like the LV style set when you're doing stuff like this for custom drawn polygons. You have to do it in a slightly different way, which is a little bit annoying from a readability perspective, but it makes sense visually, so it's not too big of a deal. So we've got this gear background, and we have to set the background color, and we do the background opacity. OPA cover is 100%. It's like full opacity is cover. And the border width, because otherwise it would have a border on by default. So we just get rid of that border. And then we draw that canvas using those points, using that style. So we draw onto the canvas the points. And that's it, really. And then we've got the label itself. So we've got the gear label, and this is the thing that was defined globally. So it's like the little N for neutral currently. The style, again, you've seen a few times now. So we create a new style for this gear text. It's the bold 80, and it's got the amber color to it. We set the label to neutral, and we set the style to the label, and we align it 190 pixels direct south of center. So this one will be in the middle again. And that is basically this entire design done. There were a couple of things that I was planning. So I had this idea of putting a red marker on the screen that was going to show me when to shift up gears when I've gone into the red line. I'm actually going to do that a slightly different way that we're going to look at now, because I've realized that's probably not the easiest way to, spot it. And I'm not really going to be looking at that for redline shifting anyway. I drive by ear, so I shift based on sound as opposed to using the red dot. But I've got a cool way of visualizing it. And the speed limit of the road that I'm currently on is a thing I'm going to add down the line. So I'm just not going to add that bit for now. What we want to be able to do instead of having this is if I am in the red line, so this is at 8,000 RPM now, the color shifts to red. And if it's below the 6,600 RPM, it shifts back to amber. So we need to have a function that will allow us to change what the RPM is. Because at the moment, we've just set it as a value. We need a function that allows us to set the RPM, and it will set both the angle of the arc correctly plus the number correctly. And we can do that with this fun new function that I've added at the top, which is update values. So there's the update RPM and the callback. I've now set RPM to be a global integer that we can access from multiple points of the code. It's just going to make things a lot easier. So we initialize it as 0. Also, the RPM frequency. So what's going to be important here is how often are we updating the RPM value that's sent through. It just means that we can match any animation of the movement of the arc with the value that it's coming through. Now, if we were to be taking it from the ECU, it can generally come out at about 10 times a second, or 10 hertz, or 100 milliseconds, depending on your flavor of units. Whereas if we're taking it from the GPS module, my GPS module will do it at 5 hertz, so every 200 milliseconds. And I'm probably going to be doing this speed for the most part from the GPS. So I've set my RPM frequency, how often it updates, as 200 milliseconds or 5 hertz. Then, if we just ignore the callback for now, we've got this update RPM function that I can call from anywhere in the code and pass it a new RPM value. So as and when I get to the point of adding the extra code into this to receive the data both from the GPS and from the ECU, wherever it might be, we can just run update RPM with the new value, and it should run through and just animate properly and change all the text properly. So what we do is create a new animation, and we just called it A, nice shorthand. We initialize that animation, and the animation is being set on the RPM arc, so the orange arc. We're going to set the value, and we're going to get the value of the arc, and we're going to set it to the new value. This is just how we have to do this. Weird, but there you go. Then we'll set the time. So how long does the animation take place? And if we're updating it every 200 milliseconds, the animation needs to be finished in 200 milliseconds. So it needs to have reached its new point and ready to go again. Then execute the callback. So that's this callback above. So this is the animation callback. We'll get to that in a second. And then the path of the callback. So is it a linear? Is it an ease in out? I experimented with a couple, and I found that linear was the most realistic and the most smooth, and it just got me up and down the values best. Ease in and out felt like it was dragging behind a little bit. And then we start that animation. So what the execute callback does is when that new value comes in, we execute the callback and set the value of the arc to the new value, which causes the animation to kick off, and it animates from where it is now to where it needs to be. And it's pretty simple. So these two things together mean that when I send a new value to update RPM, it animates that really quickly to that new point. And it does all that 5 times a second. Whereas if we go further into the function, if the new RPM is greater than our redline value, we set the arc color to red. If it's less than the redline value, we set it to amber. And that handles that color change really, really easily. Nothing else is needed. The final bit is the text label. And like I said, it needs to be characters. It can't be an integer that you just pass it. So what we've done is created just a static character, which is the RPM text. We transfer that integer of the new RPM into the RPM text. You just have to use smprintf to convert the integer into a character properly. And then we set the text of the label, so the RPM label, to that new text. Dead simple. And then the RPM, the value we've got stored globally, becomes new RPM, which we obviously need a bit later on. So what that means is when I start the application, if I do update RPM and send it a value of, say, 3000, and then upload that, we should see what the arc looks like at 3000 RPM. So there we go. You can see it's bang on the 3000 RPM marker around the outside edge, and it's showing 3000 RPM on the text. But what about if we go over the redline value and we go up to 7,200 RPM? As expected, it's gone over 6,600, so it's turned red. That's exactly what we wanted from this functionality. It's going to make it dead easy out of the corner of the eye to be like, oh, that's red, change up. Though, if you haven't heard it by the time you hit in 7,000 RPM, you need to have your hearing tested. So that's basically it for this gauge. There will need to be another couple of small functions that replicate this update RPM. So there'll be an update speed, which we could just add in here, which will have a new speed. And it's basically just a carbon copy of this bit here. And it's going to update the miles per hour. So we could just do, make a static here of the MPH text. And then bring the new speed in. And then that sets, instead of the RPM label, it's the MPH label. And that means I can just use update speed from any point in the source and update that 85 to the appropriate speed. And the final one is just going to be update gear. And it's going to be a new gear. And very much the same. So gear text. And that's just new gear. So I can send that either as a string or a number. It'll probably be a character already. So chances are this is actually just going to be a character of new gear. And then I'll just have to not do the conversion. But I'm not going to bother with this now. There's going to be a whole separate video that comes in the future that looks at how we are able to handle processing data that's being sent from various sources really quickly, you know, several times a second, and updating multiple things because it's going to be quite memory intensive, and we need to make sure that we can do things concurrently. And it's going to be a clever little solution, but we'll tackle that at a future point. For now, this is all the code that I have for creating this doody little custom gauge. And what's I think is quite nice about it is if I decided that I wanted it to be blue, I could just come into the palettes, change my amber to red, green, blue, and let's just do 250 here. And in fact, if I just make these like let's say 120 both, and then I could change my red line up to 7,200, change it to 9,000 RPM, and, you know, make this a little bit thinner. So, I don't know, 14 pixels. And that would just very quickly change the whole dimensions of everything. One thing that might be a better way of doing it is instead of having 50 here and having it always in, is make it relative to the line width. So again, it flows really nicely. So it'd be better to have RPM line width about 12, I'd say, and that just makes things a little bit more customizable. So if we just take a look at what this looks like, there we've got a slightly new design. Everything's a little bit thinner, and it's now split into 9 segments as opposed to being split into 8, and it's all just figured it out and done it automatically. So it's not just the speedo that you could use this for. Like I say, if you wanted to use it for a I don't know, a boost gauge or an oil pressure, whatever it is, all you need to do is come into these settings, change the maximum and the minimum values. It becomes a really versatile bit of code for making custom gauges. If you do want to get your hands on this code to take a look at it yourself, I will put a link to a repo in the description where you can download it. This whole environment is set up very specifically for these 2.1 inch wave share 480 by 480 ESP S3 boards. If you're not using those boards, this code won't work out of the box, but you can get your setup however you've got it and basically just include all of this code out of this build UI bit, put it in there, and it should work so long as you've got LVGL set up correctly. When it comes to the next steps of doing this with my 350Z, my new screens apparently have just got through customs, so they're going to be here in the next few days. So the next part of this, where we go on and we build screens 2 and 3, will be done on the actual screens that are going to be going into my 350Z. Like I said at the start of this video, this is a kind of a new format of how I'm going to be breaking down code going forwards. I think it's just a lot cleaner and more efficient than typing it out and you watching me type code for several hours. You have to let me know what you think of it and if you think it's a good format for this kind of stuff, because I want to make sure you get the information that you need as well as being able to make, you know, quite interesting videos. If you have any questions about the code or the application, or you want to know anything in more detail about LVGL, do let me know in the comments. I make sure I read everything and I will get back to you as soon as I can. Otherwise, whatever you do with the rest of your day, folks, have a wicked one, and I'll see you in the next video where we're going to continue and build these next two screens. Take it easy, peeps. Bye-bye.